Hello. We're going to do a little bit of truss analysis today. As you can see, I have a lovely little Warren truss on the screen. There are different kind of nicknames for different types of trusses, but this one's called a Warren truss. And it's because, well, it's not because, but one way you can identify it looks like a W in the middle, so it's a good little memory trick for finding a Warren truss. Let's see, we've got symmetry. We have 5 truss panels. We have how many members? 1, 2, 3, 6, 8, 11 members. And it's a simply supported truss because we've got a pin and a pin roller. All right, what we want to do is practice our truss analysis with some methoded joints. So what I'm going to do is I'm going to turn down my truss members and the little dots that remain, right? Those are the nodes or the joints or literally the pins. Um, Pin connections in the real world, right? Those would be through bolts connecting everything together. And what I'm going to do is I'm going to go ahead and I kind of made some bigger ones, Okay, so as we're thinking about using the method of joints, we want to create a map that we can use for all of our accounting. This is by far my best recommendation for truss problems. Okay, we need some dimensions on our truss. So what we see is that all 11 members have the same length, which is 10 feet. So they all have the same length. And all of the angles in the truss are 60 degrees. So all of the panels are equilateral triangles. And I'm going to go ahead and also kind of turn that down, get that out of the way so we don't have to focus on it. The loads we want to put in, I just loaded it with 3 4-kip forces, nice and symmetric. And I think we're ready to go with our analysis. One little trick for trusses, but all kinds of structures, is this idea that symmetry can be used to your advantage. So I've got a symmetry line set up here in the middle of my truss. And what that's going to allow me to do is work on one side, and then all the vectors I draw will be also on the other side. So that is how I am going to approach this problem. We're going to start off with, we need to do our global reactions. So turning on symmetry, we know that at A, I've got a pin support. So I could get a up or down reaction. Same thing at B. And at A, I have the potential to develop a horizontal reaction. And since I had my symmetry line, I got to make sure I come over to B and erase that, right? That's the only thing about this truss that isn't symmetric. But in terms of the force flow, I know that AX is equal to 0. So it has a potential to develop a reaction, but it's not going to do so because there's no horizontal loads in the system. So if I had a reaction there, I wouldn't be able to do the sum of the forces is equal to 0. Simply supported truss, I can deduce that my reactions are upwards. I would call this one A sub y. This one I would call B sub y. And I could do a moment equation to figure this out, but I'm going to use symmetry. So I've got 4 times 3, 12 kips down all up here. Since everything is symmetric, I know that I'm going to get 6 kips up and 6 kips up on both sides here. Okay, and if you want to prove that to yourself, all you would need to do is do a moment summation. So do a moment summation about A and prove that to yourself so that you understand why it is that we can do that shortcut whenever we're looking at symmetry. All right, we don't have to show 0 forces, so I'm going to get this 0 out of here. And I'm going to do one other shortcut. So up at the top, I'm going to say all units are kips, kilopounds, that's 1,000 pounds. And that will allow me to just do numbers. So we'll just put 6 and 6. All right, now that I've got that all accounted for, my global equilibrium, I'll turn off my supports and turn my truss members down just a touch more so they fade in the background. I labeled them before I started the video. So I just labeled them 1 through 11. And I think there's a argument for using symmetry so that, for example, members 1 and 11, I could call them both 1, but for whatever reason, just called them 1 through 11. So I'm going to go ahead and turn that down as well so we can work in the foreground. All right, I think we're ready to go. So for the method of joints, we need to find a joint that has at least one known numeric, whether that's a load or reaction, and no more than 2 unknowns. So if I look at A, I've got 1, 2 unknown forces. So that one meets our criteria. If I tried to start at C, I've got 1, 2, 3 unknowns. I can't solve that one with only 2 equations of force equilibrium. E has 1, 2, 3, 4 unknowns if you count them directly. Of course, if you're using symmetry, then it's actually 1, 2 unknowns. But as I scan through the truss, the only nodes that are going to be the place to start are A and B. So I'm going to turn my symmetry line on. I got to remember to keep it on even when I'm not in that part of the drawing, and ready to go here at A. All right, so what I do, so the way that I solve these by myself versus how I talk about them when I'm teaching is a little bit different. Okay, so if I was doing this by myself, here's the fast way I would do it. So I'd say, okay, number 2 only can give a horizontal. I've got a vertical of 6. So therefore, my member 1 has to be a push. It has to be a push force because I need to balance out that 6. Okay, so I would go in here and say 6. Um, at that point, I'm going to use the geometry to determine what this little force is, this force component. Okay, so I've got a push that represents the force of member 1 on A, breaking down into its components. And at this point, I'm just thinking of the geometry. And for these problems, you're going to either be given dimensions, lengths, measurements, or angles. So for this one, I think it's going to be easiest for us to use the 30-60 triangle sines and cosines that we've memorized, right? So all of our members are inclined with respect to the 30-60 triangle. So there's my 30, here is my 60. And we've already memorized that if the hypotenuse is 1, the short leg is 1/2, and the long leg is √3/2. Now, one of the tricks to solving this problem is not to mess with the hypotenuse until you're done solving the truss, okay? So this is a pro tip. Stay in terms of the XY components instead of converting back and forth, resultant to component to resultant to component, and so on and so forth. So here is what we can do. We've got our triangle and we've got some ratios, but what if I just double all the sides? So if I make this 2, that makes my short leg 1. And if I double the long leg, that makes it square root of 3. And so my strategy is going to be, and you could use the decimal equivalent if you prefer, right? 0.8660. I think I'm just going to use the square root of 3 for the purpose of this example. All right, so as we go back and forth, all we're going to be doing is dividing or multiplying by the square root of 3 to get the relationship between the verticals and the horizontals. Here's how that's going to play out down below. I'm going to say 6 divided by square root of 3 multiplied by 1 gives me the x reaction. 6 divided by the square root of 3 multiplied by 1 gives you the x reaction. All right, so I've got my vertical forces balanced. Horizontal forces, x direction, I have a net force to the left. Balance it out with a net force to the right, equal and opposite, 6 over square root of 3. And just like that, my first nodal free body diagram is done. So my node A is in static equilibrium. We have forces subjected to A that represent the actions of member 1, a compressive push, and member 2, a tensile pull. The next step in the process, we just start to move across our map. We're going to do a little Newton's third law. So if member 2 pulls on A with respect to 6 over square root of 3 kips, then member 2 also pulls on D with the same magnitude. So there is my Newton's third law pair. While I'm in Newton's third law mode, I usually do it kind of all at once. So I'll do the same thing for these forces. Okay, so since member 1 pushes on A, it also pushes on C. The vertical piece is a 6 kip push. The horizontal piece is a 6 over root 3 push. Okay. Now we get to pick a new node to go to, and it looks like C or D would be good candidates. Since we only have the two equations of nodal equilibrium, summation of forces x direction, summation of forces y direction, I look at node C and I'm like, 1, 2 unknowns. It's solvable. Down at D, I have 1, 2, 3 unknowns, not yet solvable. So we go to node C to do our next free body diagram. I'm going to kind of draw that node. Each one of these gray bubbles that I'm doing is a separate free body diagram. All right, so let's get in here. Let's check out node C. Let's see, I've got member 4 that can only give horizontal, member 3 that can give horizontal and vertical. So remember I said I do things kind of differently myself because I've had experience versus the way that I usually teach students. So here's the way I would usually teach students. I would have you just kind of sketch this either as a light solid line or a light dashed line, okay, and dash this one in as well. And then I would advise students to look at qualitative equilibrium. Now, the horizontal forces, so doing summation of forces in the x direction qualitatively doesn't make sense because I have 1, 2 unknowns with horizontal x direction components. But vertically, I've got 4 down and 6 up. Okay, that means I've got a net of 2 kips up. So I need a tension force in member 3 to balance that out. And I use the principle of transmissibility whenever I need to make my drawings clear and easy to read. So there's my bounding box. This is not drawn to scale, okay, but my vertical vector, I need 2 down. So 2 plus 4 down equals 6 up. Static equilibrium, summation of forces, y direction equals 0. Now I go to my ratios. I need the horizontal component of the force in member 3. And what we're doing is going from the long leg of the 30-60 triangle to the short leg of the 30-60 triangle. So I take 2 divide by square root of 3, multiply by 1. 2 divided by root 3 multiplied by 1 gives me my horizontal force component in member 3. Okay, let's make sure that this is reading as a pull. So force 3 pulls on C. It'll also pull on the other node it's connected to. And now we can do our last unknown. So what's the force in member 4? Let's look at x direction force equilibrium. And in the x direction, I've got 6 over root 3 rightward. I have 2 over root 3 rightward. So my actual force in member 4 needs to be leftward to balance that out. 6 plus 2 is 8, so 8 over square root of 3 is the force in member 4. It's compressive, a push. Now, before I go on to the next joint, because it's so easy to mix up lefts and rights, and it's really, really easy to make a mistake early in your truss problem, and then you don't discover it till you get all the way to the end and you're not in static equilibrium. Okay, so I always just spot check the node again. So check vertical, 4 and 2 is 6, that makes sense. Check horizontal, everything balances out. So I'm ready to do the next step. By the way, I have tried to remember to keep my line of symmetry on. And so that symmetry line, obviously the numbers are backwards, right? Mirror image. So we have to take that with a grain of salt. But the picture showing the pushes and pulls, that's legit. That's legit. So if you are using a tablet and can take advantage of symmetry, I think that's a good way to think about truss problems. Okay, we've got 2 nodes down, and let's Newton's third law it. So we had just solved the force in member 4 is a push 8 over root 3. It pushes at C. It must also push at E. So 8 over root 3. We can also do our inclined force in member 3. It pulls on C. Therefore, it also pulls on D. Oops, I just realized I didn't have my symmetry line on. So I'm going to trace this. See that? Tracing it with my symmetry line on to get it on the other side. Okay. All right, keep the symmetry line on. Here is my, going back to this Newton's third law for member 3. Okay, so member 3 pulls on C, it pulls on D, arrow away from the node, the free body is the node, and break that into its 2 components, upward and leftward for D. The upward we said was 2 kips and the leftward 2 over square root of 3. And we have a choice here because we could solve node D. We could solve node D because there's only 1, 2 unknowns. We could also solve node E because there are 1, 2 unknowns. In fact, with the line of symmetry, it's actually 1 unknown. Let's go ahead and do, let's just do node D. They're both solvable, but D maybe is better as a teaching tool because it's a little harder of a node. And let's work through our process. All right, I've got 2 unknowns. I've got something happening here in 5. I have this line of symmetry. I have something happening in 5. I have something happening in 6. 6 only can give a horizontal. 5 has a horizontal and vertical. Let's look at vertical equilibrium. Vertically, I have 2 up that needs to be balanced out with a component here in my unknown force 5. 2 up balances with 2 down. I'm going from the long leg of the triangle to the short. Okay, so this is a push towards the joint. So that 2 down is a push force, compressive force, compression. 2 divided by square root of 3 gives me the short leg of the 30-60 triangle. Okay, I've got my vertical forces all sorted out. That looks good. Now we check our horizontal forces. So I have this to the left, I have this to the left, and I have that to the left. So the force in member 6 has to be a rightward force. That's a pull that's equal to the sum of the three vectors that I just circled. 2 and 2 is 4 and 6 is 10. So this pole is 10 over root 3. I'm going to zoom back out. Hopefully, if I had my symmetry line on correctly, more or less. Everything on the right side is more or less there. I'll just trace over this resultant and trace over that resultant. Okay. Okie doke. And like I said, every time I complete a node, before I just quickly go to the next one, it's so much easier to catch an error as you go than have to go debug it later. So I just spot check the joint. Vertical, 2 and 2, great. Horizontal, 2 plus 2 plus 6 is 10 over root 3. That balances out, good to go. Okay. I don't have to do Newton's third law between D and G due to symmetry. So it does look like I'm ready to go to our final node, node E. And the cool thing about the method of joints is that your final calculation can be used to check your work. Here's what I mean by that. We'll do our Newton's third law thing. So we have a push here. And so we need a push here. Got my line of symmetry on. There's my bounding box. Break it down into components. So 2 over root 3 for the horizontal vectors. The upward pushes are 2, just matching that from Newton's third law. As we zoom into our final node, we don't have any unknowns to solve, but we can spot check static equilibrium. So this is our final check. Horizontally, these two balance out. These two balance out. So my horizontal force equilibrium looks great. Vertically, I have 4 down, and I have 2 times 2 equals 4 up. So I've satisfied my equations of equilibrium for that joint as well. Okay, so this is our finished map of the truss. Map of the truss. And what do I mean by map? It's just a way that we can do all of our nodal free bodies in a way that's nice and fast and organic. The last thing, like in terms of reporting final answers, this is the kind of thing that we would want to do. Okay, so if someone asks us, move this over just a little bit, get a little real estate. Okay, so someone might say report reactions. So we could say AX is 0, AY equals 6 kip upward, not A, but B, Y equals 6 kips upward. So that is what we want to do for our reactions. You can also use positive signs for this. And again, we're always doing X and Y this way and this way, unless it's explicitly stated otherwise. So someone said, tabulate reactions, give me a final answer. That is what we would want to write for that. And similarly, if someone were to say, we need some internal forces, then we would say something like this. I'm going to make my member labels be a little more prominent here. Okay. All right, so what I would do is say the force in member 1 is equal to the force in member 11, equals. Okay, so here's, put my symmetry line back on. Okay, so here is member 1 and member 11. And what we see is a push force. Okay, so we see a push force. We know it's going to be compressive. And at this point, we can go back to our triangle. So we could either use ratios to get the hypotenuse here, right? So I could find the short leg and then double it to get the hypotenuse. That would give me the resultant force. Or I can use the Pythagorean theorem and just do the squares of the two pieces. Maybe I'll do kind of demonstrations of both of these so we can see how it works. So here I'd go like 2 squared plus open parentheses 2 over root 3 quantity squared, and then take the square root of all that, okay, equals some number. I'm going to pause the video and come put these back in because I haven't run these through my calculator yet. Equals some number, and then it's going to be units of kips. And to show that it is a push force, here it is best to say either compression or tension with a parenthetical note. So since it's a compressive force, I put a C in parentheses. Do not, please do not try to use an arrow to communicate the sense of an internal force. It doesn't make any sense because if you were to go on your solution and copy this arrow, and like instead of doing this, do like this, well, that doesn't tell me anything because I just as easily could have copied this arrow, right? So showing that arrow in isolation for internal forces is meaningless. So we switch out our notation to compression versus tension. All right, I'm going to go through and set up my calcs, and then I'll pause the video, do the calcs, and fill in the blanks. All right, we've got, let's see what else we need to do. Turn my symmetry line on. All right, we could do these two members. So this is the force in member 2 and the force in member 10. The force in member 2 is the same as the force in member 10 equals, and we can just get this directly from the drawing, right? So we'll just say 6 over square root of 3. Units are kips. And then we see that it is a pull, arrows away from the body. We see that it is a pull, arrows away from the body. So we'll want to express our final answer as a decimal to 3 sig figs and indicate that we know that it's tension. Okay. After that, we could do member 6. Member 6 stands alone, right? It doesn't have a symmetric pair. So we'll do the force in member 6 is equal to, and it's a pull, and 10 over root 3. So 10 over root 3 kips equals decimal equivalent kips, and a pull means tension. Okay, what other ones are we missing? We need our top chords. So these two, this is 4 and 8. 4 and 8. Turn off the dimensions. Force in member 4 is equal to the force in member 8 is equal to, and we have a push of 8 over root 3. Compression. Okay. Which ones are left? So I did 1 and 11. I did 2 and 10. I did 6. I did 4 and 8. Okay, so the next one that I'm going to do is 3 and 9. 3 and 9. Okay, so here's 3 and 9 right there. So I'll write the force, ooh, too heavy. the force in member 3 is equal to the force in member 9 is equal to, okay, arrows away from the body or arrows away from the node, those are pulls. And we're going to have to do the scaling. So I showed you like the Pythagorean theorem approach here. Here, let's use the ratios. So all we need is the short leg and then double it to get to the resultant force. So I'm going to say 2 over square root of 3 times 2. Okay, and that's going to give me this final answer. And the members 3 and 9 are both poles, so we would report our final answers there as tension. Last but not least, we have members 5 and 7. Force in member 5 is equal to the force in member 7. And take a quick look. So we have push forces everywhere. So we know these are going to be in compression. And let's use the same ratio trick. So double the short leg. So 2 over square root of 3 times 2 gives me my answer in Kip's sine of compression. Okay, now I'm going to pause the Zoom and pull out my calculator and calculate it. All right, I'm back. As you see, here are the calculations. We do want to report these answers not in terms of radicals, but with our 3 sig figs and decimals. As I was going through it, I did catch an error. I bet you caught it before I did. But I think I had maybe looked at the mirror image and gotten confused or something, but for these two inclined members, members 1 and 11, I put in 2 instead of 6. So that got fixed when I did the number crunching. All right, so this is how we would want to report those final answers. I have one other thing to show you. Trusses, when you solve them, should make logical sense. There are patterns that happen. So what I did in this last step is I did a plot of all of these different internal forces. So I'm using the blue color, the dark color for compression. So I'm using this color for compression. And I'm using the brighter pink color for tension. And what I'm showing is just kind of a plot of the amount of axial force in each member. So over here, member 1 and member 11, right? I tried to draw this roughly to scale so that that width is 6.93 kips relative to this one, for example, that's member 8, 4.62 kips relative to this member, which is only 2.31 kips. Okay. And I just eyeballed it. I eyeballed it, but I tried to draw the ratios properly. And yeah, they should make sense. When you're first learning about trusses, you may not recognize the patterns at first, but as you get better and better at solving these, if you do a little reality check on the plots, a wrong answer will jump out at you because the pattern will look strange. Okay, that's the end of the video. I hope this was helpful. Have a great day and happy trussing.